This is a program on the preservation of Canada's northern and transportation infrastructures, and the main supervisor is Guy Doré, professor at the Department of Water and Civil Engineering at Laval University, and unfortunately was not able to be with us today because he's working in the field and just adding some last instrumentation to one of our roadside in Quebec before the winter settled down. And my PhD, it will be part of the ARQULUK program. That's why I will be presenting for him today. So ARQULUK means, in Inuktitut language, bumpy roads. And it's a cooperation research and development program financed by NSERC. And this program is made in collaboration with 12 partners from private and public sectors from all across Canada. So we have as many partners from the east and the west of Canada. And the main goal is to improve current adaptive methods beneath transportation infrastructures by developing expertise for mitigation, permafrost, and stability. So construction of roads, airways, or airstrip in the north will unavoidably affect the thermal regime of the ground. So to find cost-effective solutions, the program has been based on 4 main objectives. So the first one is to improve the knowledge of factors affecting the thermal regime under our transportation infrastructures. The second one is to improve our investigation techniques for detection and characterization of unstable soils, and as well as embankments. And also within the ARQULUK program, we want to develop guidelines for the application of different construction and maintenance strategies based on the cost, the feasibility, and the effectiveness of applicable solutions. And finally, we would like to develop a practical framework and engineering tools to support the design and the management of transportation infrastructures on permafrost. The program has been divided in 3 different themes, which are understanding the processes, detect and characterize sensitive permafrost, and stabilization strategy. These themes are divided in a way that will help the involvement of graduate students through master's and PhD projects. And all of this project will start with the state of knowledge and end with the development of engineering tools, such as calculation tools, guidelines, and methods. But to do so, there's two different paths that we can follow depending on the team that we are. So all the projects in Team 1 will be characterized by behavior and performance monitoring, and all the teams and all the projects in Team 2 and 3 will follow the path that is characterized by the development of concepts, laboratory and numerical simulation, as well as experimentation. The ARQULUK program started in April 2012, and it will be an ongoing 5-year program that will end in 2017. So I'm going to talk more about all the projects a little bit later in my presentation, but this is the timetable. I just want to show you the progression of all the projects so far. So the red line represents where we are right now. So in theme 1, which is the improvement of knowledge, we have one master project on experimental test site monitoring that will be in Beaver Creek and Tassiowac, and it will start in January 2014. We have an ongoing PhD project that just started. In Team 2, which is the identification and characterization of permafrost, we have an ongoing project on geophysical and thermal methods. There's a master project that will also start at the beginning of the summer about profile analysis. We have an ongoing master project on odometric testing. And we have now a new project about the mechanical behavior of marginally frozen soils, so we're still looking for students for this project. And in Theme 3, which is about the development of adaptation techniques, there's an ongoing master project, and there will be a PhD that will start this winter about guidelines and strategies of risk management. So I'll talk about most of the projects that are in this table, but I would like to let you know that we have now other projects that are associated with the ARQULUK program, but that are mainly funded by Transport Canada or Transport Quebec, for example. So they have been associated to the ARQULUK program, and I will be talking also about these projects. So the first project I'm going to talk about, it's about the development of design procedure for low-impact drainage system, which is actually my PhD project. This project is also financed by ADAP, which is a program on Arctic development and adaptation to permafrost in transition, also financed by NSERC. A lot of people have been talking about the big problem of water ponding along our infrastructures in the north. So with this project, we want to find solutions. So what should we do with the water flowing through our roads or ponding along our embankment, so which is the main point of my project. And this will involve soil temperatures as a function of water flow. So we want to find a relation between the water flow and the heat directly transferred to permafrost. This project also involved thermal modeling and laboratory testing, the development of criteria for allowable convective heat transferred. So what is the maximum heat flow that we can accept, for example, in a culvert before permafrost start to be degrading. This project will also involve the development of mechanistic index, such as water flow heat index, and as well as transferred function to convert water flow to heat transferred potential. And finally, it will involve development of a particle engineering method for low impact drainage system. So this is an associated project to the ARQULUK program that I was talking about. This project is financed by Transport Canada. It's about the thermal regime around culverts. So the main goal is to identify K factor for an optimal drainage system. So what we did this summer, we instrumented 2 culverts in the Yukon, one which is at the Beaver Creek experimental test site, and we have another one very close to the Alaskan border, between Beaver Creek and the border, in fact. So we had thermistor cable at the top, on the side, and at the bottom of those culverts. We had air temperature sensors inside them, and we had also pressurometer installed upstreams of the culvert. And the first culvert that we instrumented was at the Beaver Creek test site, so it's a culvert that was already in place, so we have to get in the culvert, drill in a really small place, try to stop the water flowing through. So it's been a really great experience, and much more complicated than what we thought. So the second culvert that we decided to instrument was during the reconstruction of the Alaska Highway, so they were changing one of the culverts, so it was so much more easier to add all the thermistor cables. And this will help us to quantify the effect of several parameters, such as culvert diameter, what should be the diameter we should always, most of the time, use for our infrastructures. The embankment height, should we use or not insulation? If yes, what will be the proper design for insulation on their culverts? We would like to, we'll get more information about water flow and air temperature as well. The third project is it's an ongoing master project. It's about the detection and characterization of massive ice. And this project is based on numerical simulation using the geophysics method of microgravimetry to find significant soil densities anomalies representing massive ice. So here, this is a really good picture of an ice wedge that have been taken during the reconstruction of the Alaska Highway, not too far from Beaver Creek, in fact. So mainly, as you can see here on the graph, when you do a microgravimetry profile, you will find negative anomalies where the ice features are, because the ice has a lower density than the surrounding soil, so it's about half the density usually. And this project will be also joined with another method, which is the thermal profiling, that consists of measuring the temperature at 50 centimeters depth every 1 or 2 meters. So I add, this is a graph that I've been done with them. It's a simulation. So above all the ice wedge, we should find the thermal anomalies. So which means the soil at 50 centimeters will be colder than the soil around the ice wedge. And we have also a drilling campaign that will be probably done next spring to confirm the anomalies that we found. And the fourth project is about in situ toss and element measurement of permafrost. This is also a master ongoing project. So everybody knows now that it's very expensive and difficult to get frozen samples and to bring them to the labs that are usually in the south. So there's a prototype that's been developed at Laval University to measure in situ the consolidation properties of permafrost. So this testing prototype will allow the thawing of permafrost inside the odometric core barrel. So then we'll be able to measure directly on the side the properties, the consolidation properties of permafrost under different vertical stresses. So here you can see some pictures of the prototype that we have in Quebec City, but unfortunately I cannot talk more about this because we're waiting for a patent, so I cannot give more information about this prototype. This is another master ongoing project that we have in the ARQULUK program, and it's about the thermal stabilization of transportation infrastructures using albedo surface. So the main issue here that we have to deal with, it's the heat absorbed by dark paved surface. And white paint has been widely used in research so far since the 15, but for few important technical issues, it has never been used widely on highways. These main issues are the poor durability of the paint, the high costs related to the paint, there's a low skid resistance, and it's also a dazzling surface. So this research will approach the problem from a material specification point of view instead of only considering the color of the surface. So at the Beaver Creek test site, there is 4 sections tested. So in the back here, we have bituminous surface treatment sections that use light color aggregate. And here we're testing cold patch that is a material that is usually used in the north for maintenance, patching the holes. And here we have a product developed by La France and a product that developed by Nippo, which is a Japanese company. So these 2 products are mainly kind of a marking paint that they add particles in it to give good textures. So here's the first results that Simon obtained for this site. So in black, we have the cold patch section. In gray, the light BST, in blue, the Nippo product, and in white, the La France product. And here you have the albedo, that's values that Simon measured in the field. And here he is comparing the temperature measured at the surface, so just below the bituminous surface treatment surface. And we can observe that there is quite a big difference in the temperature measures during the summer period in 2012, and there is even a difference of 7 degrees Celsius between the cold patch and the product developed by La France. However, during the winter, there are almost no difference between all the sections because I think one of the main reasons is the Alaska Highway is covered by ice and snow most of the time during the winter, so we don't see any difference in the temperatures. And this project is about the monitoring of thermal and mechanical behavior of the access road to Salouet Airport in Nunavik. This is an associated project also to the ARQULUK program. and it's financed by Transport Quebec. The access road in Salouet has been completely reconstructed in 2012, and to thermally stabilize the road, they add a thermal drain, which is a geomembrane that has been developed at Laval University. And the heat drain allows the heat circulation directly at the bottom of the embankment. So mainly during the winter, the heat will be conducted directly to the drain, and it will travel up by convection, and the heat will be expelled out by the chimneys included in the drain. And I would like to let you know that this project is also done in collaboration with the team of Michel Allard in Quebec. And to monitor the thermal regime at the test site, more than 100 thermistors were added on vertical cables. And there's also 2 series of optic fiber that were placed horizontally in the road to measure the temperature, which is new, that we never used that technology before. And to monitor the mechanical properties of the road, vertical and horizontal anechometers have been placed along the access road. And this project are the projects that I haven't started yet, so I didn't talk about it, but just to let you know that there will be a master project starting in January 2014 about the development of engineering's parameters. There will be another master project starting in May 2014 about the analysis of longitudinal profile of existing pavement. There will be a PhD starting also in January 2014 about the risk management guidelines and strategies. And we still need to find one more student for the last project about the mechanical behavior of marginally frozen soils. So to conclude, the ARQULUK program will generate expertise and know-how that all the communities in the north will be able to use, as well as the companies working in the north. And I would like to thank all our partners and collaborators of the ARQULUK program. And I would like to let you know also that there will be a course given at the Yukon College on the advanced course on permafrost engineering applied to transportation infrastructures. This course is given by Guy Doré and also by Chris Byrne. It's the 4th year that the course is given, and it's always in May. It's a 6-day course, and it does include 2 days in the field. So there will be a field trip along the Alaska Highway where we see different sites of where permafrost degradation have been observed along the Alaska Highway. So if you have any question about the course, feel free to ask me any question or to contact directly Guy or Stephen Mooney at the Yukon Research Center. Thank you very much.